Indeed, thank you all for coming. It's absolutely fantastic to see so many people here for the very first Astronomy on Tap. As Elaine said, I'm going to be talking to you guys about looking for life on other planets. Specifically, though, I'm not going to spend my time sort of doing a sort of Where's Waldo of where is ET and why haven't we found him or her yet. But rather, what I'm going to be talking to you about is more what, as astronomers, we think about when we think about searching for life, searching for extraterrestrial intelligence, what we call SETI. But in order to talk about extraterrestrial intelligence, in order to talk about searching for life elsewhere, we need to kind of begin by first understanding where we sit in the grand scheme of things, the grand scheme of the Milky Way of the universe. So that's where I'm going to start with us today. And so this is it. This is home. This is the Milky Way, or rather, this is the best estimate that we have of the structure of the Milky Way, according to all of the latest research being done in that area. We're just here in what's called the Orion spur of the Sagittarius arm of the Milky Way. And it's precisely because we are where we are that we don't know for certain if this is exactly what the Milky Way looks like. And the reason is because when we look at other galaxies, their structure is very apparent. We can see that, for example, Andromeda at the bottom and the Pinwheel galaxy at the top have a whole host of spiral arms. We can see how tightly they're wound. We can see the colour of these galaxies over their entire distribution. But when we look at our own galaxy, we can't see those direct details immediately. And the reason for that is because we see our own galaxy from a very, very different perspective to what we see other galaxies, namely this perspective. This is the Milky Way as we see it. And the reason is simply because we are embedded within the Milky Way. And the outcome of that is not that we can't tell what the structure of the Milky Way is. It just means that we have to be a little bit more conscientious in figuring out how we determine the structure of the Milky Way. But more than just being edge-on to the Milky Way, there is another additional problem that makes it quite difficult to determine the shape and the structure of the Milky Way. And that's that because we are where we are in the galaxy, our understanding of parts of the Milky Way is being blocked by the fact that the Milky Way is right in our face. We're being blocked from seeing the distant parts of the Milky Way by the structures that are in the foreground. So there's a neat way of thinking about this. Imagine that you're going to a huge art fair entirely about umbrellas. And when you go to this thing, you hear that this umbrella show is going to be absolutely fantastic. So you try and get there a couple of million years early. And you find your spot, you sit down, and just before the entire show begins, one of the umbrellas opens up right in your face, right? Now, bear with me here. Now, it's great, and you're really happy that you can see one of the umbrellas, but you kind of also like to be able to see the other umbrellas, right? Now, I see people nodding over here. That's what I like to say. Right. And so essentially, we're being blocked from parts of the Milky Way. That was a very convoluted example. Bear with me. All right. So this is the Milky Way as we see it. This is a picture from a survey called Gaia, and it's the deepest or the most thorough survey of the local area of the Milky Way that we've done to date. But even with an extremely new, recent, and thorough and deep understanding of the Milky Way, we still only probe about 1% of the Milky Way stars. And they occupy roughly this sort of area here. And part of the reason for that is because when you try and look deeper, you see so many stars that they start to get in each other's way. The density of them is so high that we can't actually continue to see what we're trying to see. And the other reason is because, like what I just said, we have all these big streaks of dust and things like that that are in the way, blocking our view of other parts of the galaxy. But nonetheless, even with what we can see, we can estimate the number of stars that there are present in the Milky Way. And that estimate is currently between 100 and 400 billion stars in our galaxy alone. And this fact brings up another problem. But it's not an astronomical problem, it's a human problem. And that problem specifically is that of large numbers. The human brain, put simply, is fundamentally incapable of comprehending large numbers. The way in which it functions does not allow us to do that. And so, in order to sort of understand this a little bit, I'm going to start by everyone just kind of imagine an arbitrary object. It doesn't matter what it is, be a coin or a potato or whatever. Just imagine that one object, see it in your mind. Now I want you to see 1 billion of those objects, just in a big pile, right? Everyone got that visualization in their heads? Right, that pile that you can see in front of you, that mound of 1 billion objects, is absolutely too small, right? Fundamentally too small. And there's a really simple way of demonstrating this that was going around recently on social media. And that's the following. Everyone knows what the period of 1 second is, right? That's something we deal with on a daily basis. I'm now going to tell you that 1 million seconds is about 11.5 hours, okay? I now want you to guess, from knowing that fact, how long 1 billion seconds is. And we're going to do a very simple straw poll. I'm going to get people to raise their hands, okay? Who thinks that 1 billion seconds is less than a month? Okay, couple. Who thinks it's less than a year? Okay, a few more. Who thinks it's less than 10 years? Okay. Who's too introverted to raise their hand in a public setting? Excellent. Fantastic. That's what I'm talking about. Right. So 1 billion seconds is just over 31 years. Right? And that is just it's a simple way of understanding or of demonstrating that the human brain just doesn't function when it comes to large numbers. And it also explains and it also demonstrates how difficult it is to discuss these sorts of numbers with people, to discuss these things and visualize these things in a day-to-day discussion like we're having here. If we had, so the Milky Way has 100 billion stars. If we had a stack of paper that was 100 billion sheets tall, then the men and women aboard the International Space Station could reach out and take a piece of paper off the pile, and that piece of paper wouldn't even be 1/10 of the way to the top. If that stack was made of Lego bricks that are 9 millimeters tall, that pile would extend 2.5 times the distance to the moon. Right? So in summary, stars. Yeah. Right? Lots and lots of stars in the Milky Way. But why are we talking about this, right? What does that even matter? Stars aren't the reason that we're here. Stars aren't the reason that we want to talk about this stuff. We want to talk about extraterrestrial intelligence. But stars are a really good starting point because they give us a good idea of the sorts of numbers that we're dealing with. They give us a good idea about where we sit in the grand scheme of things and where we sit in the galaxy. We now want to start folding in other details. We now want to start talking about other important factors that are important when we start thinking about extraterrestrial life. And we have developed over a very, very long time an excellent means of adding in additional details to these sorts of things. But unfortunately,
I'm afraid we need to use math.
Right, so this is what's known as the Drake equation. It was developed by a guy called Frank Drake, an astronomer. And it's a really, really good way of quantifying the number of detectable extraterrestrial civilizations that we expect to find in the Milky Way. Okay? Now, it looks a little bit fearsome, but it can actually be broken up into 4 reasonably simple sort of understandable parts. And so we're going to look at these 4 understandable parts one at a time. The first chunk, the first three terms, can loosely be described as explaining the number of habitable Earths that there are present in the Milky Way at any one time. Okay? So recently, as of today, there are over 3,800 known exoplanets in the Milky Way galaxy. 10 years ago, it was a tenth of that. It was 340. And 20 years ago, we knew 15 exoplanets total. The reason, or part of the reason, for this extreme explosion in the number of known exoplanets was a survey that was called Kepler. And Kepler, or a mission rather, called Kepler. Kepler's mission was to try and look at a particular point in the sky. It occupied 0.25% of the sky. And in that particular part of the night sky, to try and measure the dimming of stars that was caused by planets passing in front of them. And because of Kepler, we now have, or largely because of Kepler, we now have this unbelievable quantity of exoplanets. But more than that, we can use the results of Kepler to estimate how many planets there are per star. And the results that exoplanetary scientists have at the moment is that there is roughly, on average, 1 planet per star in the Milky Way. But it's not just planets per star that they were interested in. They're interested in more sort of SETI-like goals of Earth-like planets in Earth-like situations around Sun-like stars. Okay? And what that means is that they were looking for sort of Earth-sized planets in what we call the habitable zone of Sun-like stars. And the habitable zone is this sort of region around any star where, because of both the brightness of the star and the amount of light that reaches the planet, and because of the greenhouse gas effect on a planet's surface, a planet could hold liquid water on its surface. Because as we know it, life needs liquid water. And so Kepler searched for possible Earth-like planets around Sun-like stars. And what they found was that around Sun-like stars, 1 out of every 6 stars likely held an Earth-like planet. 1 in 6. But in the context of what we're talking about, that doesn't actually completely cover the story. We want to know, with these 3 terms at the beginning of our Drake equation, what the fraction of habitable Earths is. And that doesn't just mean it could hold liquid water. It means that it needs to be able to support life. It means it has to have liquid water. It has to have a magnetic field emanating from its core to stop the atmosphere being stripped away, and a lot of other things. And so these 3 numbers encode all of that information. And that's the first chunk that we talk about in the Drake equation. The second chunk is the fraction of those habitable Earths that actually go on to form life. And this number is very, very difficult to pin down. And the reason it's difficult to pin down is because we currently have 1 example of life existing on an Earth-like planet that is habitable, and it's us. And so essentially the best estimate that we can put on this particular parameter is that it's definitely not 0. And that's pretty much it. Right? The optimist would say, hey, we're an Earth-like planet and we form life. Make that baby 1. Right? But a pessimist might say the opposite. We're a freak occurrence. That's essentially 0. Right? We'll get more to that a bit later. The third part of this equation is to do with the fraction of that life which formed that then goes on to be able to transmit its presence to the rest of the galaxy. In the Milky Way, currently, or on Earth rather, currently, we have a huge gamut of life. Life goes all the way from the simplest of organisms, single cellular organisms, through to multicellular organisms and small microscopic animals like plankton that create these beautiful bioluminescent tides all over the world, all the way through to us. But in the context of these two numbers, the only ones that matter are those which can transmit their presence to the outside galaxy, the outside universe. And that alone is us. Right? So these two numbers may not be anywhere near one, right? Given that we're the only animals that have created the telescope. And what that means is that every different non-communicating life form on the planet, every single animal that just cannot communicate with other intelligent beings. Does it? It's a cheap one, I know. They don't qualify as life in this equation. The last factor that's relevant to us, or that's important in this equation, is this Lturn. The Lturn is the time period that a civilization that is able to communicate with the outside universe continues to do so. Right? And this is not, I mean, you might naively think that this is an infinite number, that as soon as you begin to be able to create radio waves and send them into space, then you do so for the rest of eternity. At the upper limit, this is probably limited by the lifetime of a star. So a couple tens of billions of years, right? Because if your star explodes and the planet goes with it, then you're no longer going to be communicating your presence to the outside world. But in reality, we expect this number to be significantly lower. And the reason why we expect this number to be significantly lower is typically grouped into two possible main outcomes. The first of which is that civilizations destroy themselves, and the second of which is that they become so technologically advanced that reality ceases to be worthwhile, and that they go into a virtual reality and stop caring about the universe. And in both of those cases, signals stop. And now what that number is up for a lot of conjecture, and it actually leads us very nicely into the next one, which is that when we put all of this together, we get the result of the Drake equation, which is the number of civilizations we expect to be communicating with us from within the galaxy. And now, if we're an optimist, like I am, then we say we have one Earth-like planet produced every year. Life always forms, and that life always becomes intelligent, and it always begins to communicate. Then what that means is the number of sentient, intelligent, transmitting life forms in our galaxy is just determined by this L number. And if that L number is 1 million, then there should be 1 million civilizations in the Milky Way alone screaming into the void, trying to get our attention, just like we are to everyone else. But there is a significant problem with that idea, and that is the reality of our observations. Despite all of our searches, we have currently found 3 intelligent life. No, I'm kidding. We have currently found no signs of communicating intelligent life anywhere in the universe. And this discontinuity between what we expect and what we find is frequently referred to as the Fermi Paradox. There are many solutions that people have proposed to the Fermi Paradox, 2 of which are probably the most sensible, and you can group most of them within these 2 categories. The first of which is we are alone. We are the only intelligent life that exists in the galaxy. And this is what we call the rare Earth hypothesis. And the justification of the rare Earth hypothesis is that the reason we are alone is because one of these factors, one of the first 3 factors, is infinitesimally likely. It's infinitely unlikely. And we are a fluke. And therefore, it's entirely reasonable to expect that there will never be another fluke. Right? The second possible solution, the one that I personally think is probably more likely, has to do with this L value. And it is this. Life evolves too quickly for its own good when it comes to seeking out other life. And the idea is essentially this. And the reason I think that this is justifiable is just by looking around. So take the Earth as an example. We first developed radio communication. The first long-distance radio communication was made in 1901. Since 1901, we've been transmitting information out into the void. How long do we think that the span of our transmissions will continue before we inevitably no longer communicate? For one of these two reasons. Let's just go with a couple thousand years. And I think a couple thousand years might be generous. And the reason I think that is by looking around. Since 1901, we could look at nuclear weapons, as this cartoonist has done. But more likely, since 1901, we've unequivocally and possibly irrevocably changed the climate of our planet. You extrapolate that another 2,000 years, and who knows? But you don't have to be a pessimist either, right? You can go the other way. You can say, oh, that's just a blip, we'll figure that out, no worries, right? Paris Climate Accord, right? And you can say, what happened in the last 120 years technologically? Since we created the first telecommunication, whoop, I went back. Since we created the first radio transmission, we've developed supercomputers. We've developed robotic rockets. And we've pushed the boundaries, or started to push the boundaries of what we think about artificial intelligence. Is it so hard to believe that in 2,000 years, we will have created a technology so advanced that virtual reality begins to become preferable to actual reality? And if that does sound fantastical to you, it does sound like a fantasy, then I'd offer you to consider this. Today, in Guangzhou, China, there is a virtual reality zoo. There is a zoo where they have realized that it is preferable for people's enjoyment to have virtual animals than real ones. And it's because people get to interact more, and it's much easier for them because you don't have all that fuss of keeping animals in captivity. It's a much easier business model. They keep one server. You ever tried running a zoo with one animal? And so this isn't necessarily a fantastical idea. And so if we think about our 2,000 years, we think about the 2,000-year window that we have to transmit information to the universe. We think that 2,000 years is a pretty good estimate for any civilization. Then this is us. How long, how wide a view do we have of other civilizations? Where must they be if L is 2,000 for us to see them? And the answer, there. And if you didn't see anything, that's because it was a very small change. Right? But even if they're no longer existing, even if, okay, they lasted their 2,000 years and then they fell into their computers and that was the last they transmitted, the distances involved, the distances in our galaxy are so unbelievably large that the likelihood of us seeing a signal from another civilization while we are listening is almost infinitesimally small. Again, another fantastic comic. SMBC, highly recommended. How's that? But, of course, at the moment, all of this is just, it's more philosophy than astronomy. Because we don't understand what most of these parameters that we were talking about are. But I'd like to leave you with one last astronomy fact before the end of this talk. And that's that everything I've told you tonight, everything we've discussed tonight, has been about the Milky Way galaxy. It's been about our galaxy. But of course, we're not the only galaxy out there. If you take some of the most powerful telescopes on the planet and you point them in an area of the sky that is less than 1% of the total, and you look for galaxies to just a fraction of the distance to the edge of the visible universe, this is what you see. Every single prick of light in this image is a real, documented, seen galaxy. We have observed them, we have mapped them, and we have placed them in three-dimensional real space where they are. Every one with billions of stars, billions of habitable Earths, billions of places where life could sprout. And so to sit in and amongst the enormity of that which is the universe, and to think that we are alone, to me, is unthinkable. That's all.